Lecture 2, starting by my homework, coming back to this again. So I get confused with this equation last time, right? So just following up, we have a inverse Fourier transform of here, and then we're going to change the qx, qy, that's in a reciprocal space coordinate to rho theta. So that's a coordinate change, and then it goes like this. And then using this requirement, then this goes like this, okay? So up to here, it's okay. And then I got confused with this. So this is called convoluted projection. And why is that? That was where I got confused. And then before, I told you that I take the projection, and then I get the Fourier transform this, then it's going to be the Fourier intensity and phase at the same angle. That's what the theory says. And then, of course, if I take only this back to the real space, that's the inverse Fourier transform, then this one goes back to the projection, right? And then the projection can be written like this. And then the QR theta, that was previously, in my previous slide, this one, I write it down again here, and then compare these two. And this is quite similar, right? Except for this weighting function. And weighting function is in a Fourier space, looks like this. So it means that as you take many projections at different angles, and then take the Fourier transform of each projections, and then try to fill the Fourier space, then this internal part is oversampled compared to the other one outside. So this weighting function reduce the intensity, the coordinates, so to say, and that's the weighting function. So this is quite similar to this equation, except this. So this is a convoluted, convoluted by this weighting function, and then it's going to be a projection, sort of. That's where I got confused. So once you admit this, then this is inverse Fourier transform, so it goes back to the real space, and then this is real space, and then the integral is over the angle. So that's why we do the projection, and then tilt the image, and then project it, and then summing up. Okay, so that's my homework. I hope you understand.
But in the middle, it's always.
In the middle, you mean here?
Always zero. In the middle, this direction is always zero.
Here?
So the middle of the element is never
You mean
yes,
the
here.
coordinate here?
Never counted in any image.
It's correspond to the infinite large structure, right? Okay. So
okay.
Yeah, it can be zero. Okay, and other things, I got suggestion from Professor Creighton that some of you ask questions about how we're going to prepare a sample for the TM. Okay, that's microtoming, and I try to find a good schematic picture for inside my computer. This is what I get, and the whole instrument looks like this. And the size is about that. So you can put that on the desk. So it's not that big instrument. And then this part is very, very important part. Okay, and you have a sort of a swing bar, and then at the tip you have a sample. So the sample is prepared so that you have a sample, and then you embed it in epoxy resin. Okay. And then after that, you trim the surface, the tip. That's why it looks like this. and then so that the sample it appears at the top of at the tip of this sample block. And then we mount this, and then this is the knife, and here it's the knife actually. So here it's the knife, and then this is a swing bar, and then you have a sample here. What the instrument does is that you have a sample here, and then this is a swing bar. Okay, so this swings, and then you have a knife. So this knife cuts your sample, and it goes back, and then it comes back again, and then for the second time, let's say this bar proceed like 100 nanometer, or maybe 200 nanometer. That's according to what you set, okay? And then if you set 100 nanometer, then it proceeds like this, and then it swings again. So sequentially, you have sections. So that's how it works. And then to give you a better idea, this is the knife, and then this is your sample. So the instrument moves like this, and then it goes forward, and then cut it again, it goes forward, right? And then expansion of this part is going to be here. So this is a knife. One section, second section, third section. So you can keep going. That's how we make very thin layer of the sample, okay? And you have a question? Okay, how do I pick it up? That's here. So you have a copper grid, and then you actually pick it up. Yeah, indeed, pick it up.
Can it handle wet samples? Can it handle wet samples?
What sample? Sorry.
Wet samples with water content.
Hydrogel. You could do that. It's difficult because you can do that. Okay, hydrogel, but it's hydrogel. Contains water. Yeah, cryo. Yes. Yeah. That's okay. So for sample like a polystyrene, which is very solid, you can do that at room temperature. For the rubber or maybe hydrogel, but if you cool down the hydrogel, then the water inside the hydrogel crystallizes, isn't it? Right? And then destroy the structure, maybe. Could be. So you need to be a bit careful for this crystallization of the water. Anyway, so for soft one, what you can do is that actually cool down the sample. So imagine the cheese at the room temperature it can be soft, but at the low temperature it can be a little harder, right? Then you can cut it. So that's called cryomicrotoming. Or you can choose you can change the knife speed. It's a viscoelastic property, right? Lowering down the temperature and cutting with fast knife, that's a similar effect. So first choice is changing the temperature, and to optimize the result, you may want to change the knife speed. That's how it works. Okay. So I hope you have some idea about how we're going to prepare a sample. That's one way. Okay, let's go back to the topic again. So I finish when at this stage missing wedge problem for the 3D TM, and the left one is here for the instrumentation. But today I really like to introduce the example. So I would like to just skip these two, just give you references. This topic the good reference is our paper in 2005. But before going to number 4, I just make a comment. Okay, so towards the end of my talk last time, I explained this to you, right? So when we tilt the sample holder, it may hit the objective lens. So that's a physical constraint. And the other limitation is that your sample is planar. So if you tilt it, then the effective thickness increases. That's the number 2. So those are the 2 reasons why we cannot actually tilt up to 90 degrees. So for complete tomography, you need to tilt the sample up to 90 degrees. But with this, you cannot do that. And then how this constraint affect the imaging? Let's say, for example, we have a cylindrical structure of a polymer, for example, and then you have a thin layer of doesn't have to be thin, but let's say thin layer, and then your cylinder aligns parallel to the surface. This time, this kind of geometry. When we do electron tomography with a limited angle, like 60 to 60, then in this picture, we have a tilting angle here. So sorry, tilting axis. So we tilt the sample like this. In this picture, we tilt the sample like this. These are the same field of view. But yet, here, in this particular tilt, you don't have the structure reconstructed properly. Whereas here, this part is reconstructed properly, but this part doesn't reconstruct it properly. So particularly if you have a very anisotropic structure like cylinders, then you have to be careful. That's the message. Okay. Why? Please go back to the paper, and then you can find the reason why. So in this case, for very anisotropic type of sample, for example, FRP, for example, you have fibers in a resin, that sort of sample. What we do is that we take electron tomography 1, and then we change inside the TM. We change the sample. I mean, we change the direction of the sample, and then we tilt it again at the same position. Okay, we take 2 data and then combine them. Then we can have a complete set of data. So it's very tedious. But when we did that, it's 2005, so it's more than 15 years ago. And since then, electron tomography has been widely spread, and people can use it. There's a software available, and you can ask a microscope company. You can have an option of doing electron tomography. But unless you don't know this kind of problem, you mislead, you misunderstand the result. So please be aware of this. Okay. And this topic here is to eliminate that problem. So the reason why we have a limited angle is that one reason is because of the shape of the sample. Okay. So if you have this planar type of a sample, then, like I say many times, if you do this, then the thickness is getting larger, and then the image gets worse and worse. What if you have this type of sample? I mean, instead of this, instead of plane, if you have a rod, and then rod is going to go into the microscope, and then you do this, then we can do up to 90 degree tilt, because this is because the rod. So whatever I rotate, the thickness doesn't change. So that's from that we can have a very quantitative electron tomography. To make this rod sample, it cannot be done. I mean, maybe done, but it's very difficult using microtoming. You have to cut it once and then cut it twice, right? You cut the sample to make a planar sample, and then you have to cut it again. But that's very tedious. It's very, we have done that, but only a few students can do it. So instead of, in that case, instead of having a ultramicrotomy, we use FIB, focused ion beam instrument. And that's also in this article. And nowadays, when we prepare sample, you either use microtome or FIB, focused ion beam instrument. So that's something you want to know, you know. So when you have a chance to make sample, you can ask your technician or professor, should I use microtome or should I use FIB? Okay. Okay, so I would like to, you know, ask you that I finish up to here. Okay. Just if you are interested, please read the papers. And then this is a summary up to here. So summary 1 is the 3D structure can be observed on a nanometer scale by electron tomography, missing which I didn't describe very well, but to solve this, one way is just do the dual axis tomography, but that's very tedious. And in order to have really quantitative 3D imaging, then you need to have a rod-shaped sample, and you need to tilt up to 90 degrees. So that's the message. And for those who wants to know more, there's a good book from Dr. Frank, and then there are a couple of references you may want to have, and then this information will be sent to you by a PDF later on. So I prepared 3 applications today. So I try to cover one by one, and then hopefully I can finish up to here. So the first one is obviously that's the example using electron tomography, block of polymer nanostructures. That's very classic, but that's good to know. So as we know, block of polymer can be used for many applications, right? So mask for the lithography, or membrane, or sometimes electrically devices for separator. And so what we would like to do is that, for all those applications which people use is nanostructures, self-assembled structures of block polymers. And then what we want to do is try to analyze those data in detail. I showed this before. I'm particularly interested in this type of network type of structure, and historically that has been found by these 2 gentlemen, and then there was a discussion whether it's a diamond structure or the gyroid structure. And then 1994, there's a scattering paper, almost end the discussion that the structure is actually gyroid. But like I say before, what I wanted to do when I was a student is that just to image this. Okay, so we took the electron tomography. That's the raw data. It's a styrene, isoprene, styrene, triblock tarpaulin. 2-component triblock. Okay. Then I stained the sample, so the isoprene part, it's a middle block, appears to be black, and then the styrene at the edge, that appears to be white. So you can feel that when we tilt the sample, how the projection look like, because the structure is not so simple. So as you tilt, structure gets the pattern gets changed. So using this data, I skip everything, but I reconstruct the data. So this is a real experimental data, and then in this figure, the polystyrene. I only show the polystyrene domain, and this light gray beige network and this green network. Those are consist of polystyrene. Same species, and isoprene is transparent in this picture. So once we have this kind of a picture, then we can do many things. Sorry, this is wrong. This is not styrene isoprene. This is styrene isoprene styrene. Okay, so that's wrong. So what we can do is that we take a single grain, and then we do the sort of pseudo scattering experiment. This kind of sample is multi-grains, and then when you do the scattering, the beam size is typically on the order of millimeter in the lab, and even though you go to the facility, it's micron size. So there are lots of grains actually inside the sample. I mean inside the beam. Sorry. Then the scattering pattern actually from that kind of experiment will be circular. So what you can do is you can do the circularly averaged, and then make the 2D pattern into 1D pattern, and then you discuss with the peak position. That's what people do. If we take the small part, just a single grain, and then Fourier transform, that's the same thing as the scattering experiment. Then the scattering pattern will be like this, very spotty. Then we can do the crystallography analysis. Then we can determine the space group from this. It turns out IA3 bar D, that's gyroid. So we know this is a gyroid structure. And the second thing we can do is that we can actually put this data into the computer, and then we can shrink the network so that we can have this three-dimensional, how they say, thinning the line sort of image. And from that, you can actually measure the position of the junction if there's a junction, or if you find the junction, then you can measure how many branches coming out from the junction, and you can determine something like a topological measure like genus. I will come back to this. We can do the soft. Yes.
Maybe a question. Why did you choose to put in green and beige the polymer and not use the same color? It's just because you have two networks which are important.
Yes. I forgot to say that. These are the two networks don't intersect each other. So it's a two independent network. We have of course defect. At the defect, sometimes this one and this one, collide or connect, but basically these are the two independent networks. Thank you. And the other thing we can do is that we can measure the surface curvature of this network structure, and from that we can measure the mean curvature and Gaussian curvature, and then from these, we can actually discuss the packing frustration inside this structure. There's I only display surface of this phase separated structure, but actually inside there's a chain, brocopolymer, of course, and then brocopolymer inside the chain we cannot see individual chain, but with this framework we can estimate how much the sample inside the block inside the sample is frustrated. And of course, we can actually, from this kind of data, we can make a three-dimensional image, and then we can actually go into the sample and then look for a defect, for example, like this. That was this is 15 years ago data with a very inferior type of a machine compared to today's machine. Okay, so these polygons are rather big. Otherwise, we cannot move the data, but actually the data is more precise. Okay, looking at this data, it's interesting, in many ways. For example, here, sorry, I probably stopped this. Up. Oops. Can I stop this? Maybe not. Maybe not. Sorry. It's. I just leave it. Okay. For example, this domain is disconnected here, and then you have a 3 connector here, right? And then again, it's 3 connector, and then you have something strange domain there. This is, I think, irregularly connected part. So you can learn a lot of things. You know, you can find defects. You can find proper 3 connector somewhere sometimes. So, and this is again, this is not computer simulated image. This is actual data. All right. So before showing this analysis, I would like to give you the ideal structure of double gyroid. So this is a model. This is a computer-generated model. This is no experiment. And then the basics. I mean, the basic structure of the gyroid is this 3 connector. You know, if we have a junction here, then we have a 3 branch with the 100-degree angle. So it's on a plane like this. And then the next one, there comes the next one, which is also a 3 connector, but there's a twisting angle, torsion angle. So 3 connector here and the 3 connector here, but it's not parallel. It has some angle. That's how this structure has a 3-dimensional sort of labyrinth structure. Okay. So what we would like to do is measure is that try to find the position of this junction and then try to find how many branches coming out from the junction. That's the primary target. So we write a code, not me, but my student did that. And then these are the polystyrene domain, for example, and then we try to shrink it without losing the connectivity. Okay, that's what we call 3-dimensional thinning. And the result is like this. And then once we find the junction point, and then we can record the coordinate, and then and also find the next adjacent one. Then we can find the length. We can find a direct length, or we can find this contour length, and of course we can find a coordination number. Okay. That's real experimental data. This is the input, and this is the output. And then if we overlay the domain on this, then I hope that I can persuade you that resulting the thread is right in the middle of this domain. I hope I can persuade you, right? Then I just follow, from here, and then I find junction here, and then I can find this is 3 connector, and then we can do that and find another one, and we can keep on going. So the result is good, 3 connector, 90%. And there's 4 and there's 5, and we found this 4 is more or less related to the defect, and sometimes the independent 2 networks coming together, or those kind of things. So this is a direct proof that the phase separate structure is a gyroid. Okay, and this is the histogram of the junction distance. And then this is path distance, and this is linear distance. That's a direct distance, and both of them have a peak somewhere here. And this distance is normalized by the cell edge. So this peak position at about 0.3 something or 0.4, that's also correspond to the gyroid structure too. So we know it's a gyroid. Now, the shape of the structure. This is gyroid, phase separated structure of a brocopolymer. Brocopolymer is, I don't have to explain that there's two sequences and covalently attached together. This is polymer blend. No covalent bond between the A and B. And then, as you know, for the polymer blend, we can induce the phase separation. And in this particular case, we induce the phase separation via spinodal decomposition. And then we all know that in the spinodal decomposition, we have a network structure. And then this image has been taken using a confocal microscope, laser scanning confocal microscope. You can look the size. This 100 micron, 100 micron, 50 micron. Whereas here, I didn't write it down, but this is 74 nanometer. So this is much smaller than this. And for the polymer blend, it evolves. It's getting bigger and bigger. So the question is, which structure is more complicated? Can you quantify it? Some say this is more complicated. Maybe the other says that's more complicated. Can I quantify? When you go to the topology textbook, you can find a measure called genus, G. And then one way to define this genus is that here. The genus is the topological measure characterizing the complexity. A surface with genus G is a topologically equivalent to the sphere with G handles. So like this. So we have sphere here. We have one handle. That's genus G. Yeah, genus 1. If we have two handles, that's going to be genus 2. Interesting thing is that, in a topology, shape, just shape. I'm not talking about volume. I'm not talking about surface area. Just shape, complexity of the shape. If you don't cut the surface, you can change the shape. For example, you shrink this part, then it's going to be a donut. If you expand this part, and then punched from the top, it's going to be a mug cup. So topologically, these are the same genus 1. So I found a nice movie from Wikipedia. So you know that how it's deformed from donuts to the mug cup. Now, this number genus can be measured using surface curvature and also from the three-dimensional thinning result. And because we did the thinning result, we know the total number of junctions and total number of branches. So we plug it in here and then plug it there. Then we have genus. So this one here, the gyroid, experimentally determined gyroid, the genus is 7. So it's equivalent to the structure that we have a sphere and then we have 7 handles. By the way, in theory, if this is a real theoretical gyroid, then it has to be 9. So 9 versus 7, that means we have a defect. For the polymer blend, phase separated structure, the genus turns out to be 2.6. So we know that the complexity is over there. The gyroid is much complex than the spinodal decomposed bicontinuous structure. And then you are the chemist, right? Many chemists here. To make that kind of complicated structure, what we have done is just introducing the one covalent bond in the polymer, in the chain. So that makes the structure that complicated. So if you make star or if you make brush, and then I don't know how it turns out. So electron tomography may give you a way to characterize that kind of topological measure too. Okay, so for surface curvature, I think I would like to go to the next topic rather than keep going with this phase separate structure. So for those for those interested in this surface curvature measurement, please read this paper, Physical Regulator 2000. That's 22 years old, but that's our paper. So we compare with the theory in terms of the chain frustration. So sorry about that. And other examples, gyroid. And then this is the structure from the tri-block tar polymer, ABC. As your structure, I mean, the polymer gets 2 component to 3 component, even though it's a linear, sometimes you can have this kind of very strange structure. This is what we call a helical structure. You know, this is a polystyrene and a polybutadiene and then PMMA. So polystyrene makes a cylinder, and then PMMA, the end blocks, is going to be a matrix, and in between the middle blocks is going to be a helical structure around the cylinder. So this is not the sample we synthesize, of course. Somebody else synthesized it, and then they struggle with structural characterization. By doing the electron tomography, we know that there's this is a 2-strand helical structure. Unfortunately, we have left-handed and right-handed at the same time. So we cannot have a control at this moment. It would be nice if we have all left-handed and all right-handed, but unfortunately, we cannot do that right now. And this is a structure from lamella forming block polymer. If we contain the lamella forming block polymer, what the structure would be. We actually found OBDD diamond in some polymers, and in some polymers we use block polymer self-assembly to align the nanoparticles, and then for this kind of structure, the electron tomography is also powerful, and this is the same thing. Okay, let's go to the, I just skipped this, and then let's go to the next topic. So next topic is the not 3-dimensional. That's going to be 2-dimensional, okay? In situ visualization of nanocomposite under the extension. So we stretch a sample and then visualize what happens. Why we do this? We want to do this. As we know, the surface of the tire is a rubber nanocomposite, and the matrix is the crossings rubber, and then there's a nanoparticles inside. This is a typical TM picture, and in this particular case, we have 2 different fillers. One is a carbon black, and the other is silica nanoparticles. And this is a model of this thread goal, the surface of the tire. When we do the tomography, we can differentiate, carbon black, which is blue, and the silica particle, which is pink in this picture.
These are stained image?
This is not stained.
Okay,
yeah.
Not useful to stain image.
For this carbon black and rubber and silica and rubber, those has a contrast, so we don't have to stain. But you raise important point. Looking at this TM image, it's difficult to say whether this one is carbon black or which one is which. So we use. It doesn't have to be tomography. It has to be element analysis under the TM. You can do that. And then this is actually a combination of the elemental analysis and the tomography. Okay. So what the point I want to make is that so far, I mean, up until something like this, 2007, 2000 something, people in this area are using this TM picture for structure analysis. And then with the tomography, we can have additional one dimension. And then how we're gonna use this? I don't know. Okay, how we're gonna use this? One way is that you can actually put the three-dimensional data into the computer, and then you stretch the structure in the computer using what people call finite element analysis. Okay, so we have a collaboration with this company, and then we give them three-dimensional data, and then they did the calculation. Okay, so we forgot these two data. Okay, we're going to focus on these two data. So this red line, this is the actual experimental data. We have a sample and then we stretch it. And this is stress and this is strain. This is mislabeled. Stress strain curve. Okay, so this blue data, that's simulated data based on the three-dimensional TM image. So as you can see, they are different, but they are at this time, 2008 or so. This is surprisingly in good agreement. Okay, before this, they use this two-dimensional TM data to model their structure. So even though you know the aggregate size and the position, you don't know this direction, the depth direction. So if you see the particle like this, it's actually like this, or it's even farther away. They don't know that. But with the three-dimensional image, you can have this axis, z-axis too. Then after using this type of a three-dimensional data and they simulate, then the result came out very nicely. And good thing about this type of simulation is that you can actually visualize the stress or inside the sample. And this is one picture from the simulation. This black part are carbon black, and then they stretch this way, in this way. So this is a place where the stress concentration takes place. And the other part, for example, these blue parts are not doesn't experience much stress in this material. Meaning, yes. Scale is probably this scale maybe a 50 nanometer or so. Yes, and because the each I don't know which one is the individual sphere, but let's say if this is a sphere, then it's going to be 20 nanometer in diameter. So then the 50 is something like this. Okay, so that's a good thing, but there's a deviation. Why is the deviation? One thing is that the volume we put it in is it's not enough. So statistically, it's not enough. That's one reason. Another reason maybe we didn't take that a layer around the carbon black, which is called sticky layer. We didn't take that into account, and all those reasons we can foresee. But the biggest reason, I think, at the time was that we know the 3D structure here at the quiescent state, but we don't know the structure experimentally when we stretch. So up to those points are only computer-generated image and then calculation. So we need to make sure that how the sample structure is changed, and then it's corresponding to the computer simulated structure. That's something we need to do. So that's the motivation. Okay. So the result is here, and then stretching experiment under the TM has been done many years ago by Professor Kramer's group, I think Professor Creighton is involved in this, I think. Anyway, so in this case, they use ABS, I think, ABS resin. And then they stretch the sample, and then they stain the sample to fix the structure, and then they observe the fractured structure. And then from that, they discuss the mechanism of how the craze forms and how the material is damaged, so to say. There's another way. You can use this type of holder. That's a stretching holder. You have a sample. You screw this sample, and then this part is going to be going this way. So you have a pin down, and then you have a pin down, and then you stretch this way. Okay. So initially, you look at in the middle. As you stretch, the field of view is going to move this way, and then for rubber sample, you stretch like 4 or 5 times at least. Then eventually, with this type of holder, the field of view is going to be out of the scope of the instrument. That was a problem. So we make a new holder. That's a design, and so we have a base holder, which is very thin, and then we put the what we call cartridge on this base holder, and then through this there's a hole like this, and then we screw to the actuator, and then actuator moves this way, or maybe this way. So so it's similar to the previous one, but the stretching direction is different. I think I should use this. So the sample is going to be breaching like this. This is a gap. There's a gap. Okay. The sample will be sitting like this. Okay. And this whole thing is going to be mounted like this. And then this is the screw that to fix this cartridge onto the base. And this is screw which is not connected to the cartridge, but connected to the actuator. And as this screw goes this way, because the hole has I don't know how to say this in this shape. So you can take a look. As the screw goes this way, the gap opens this way. So your electron beam is always sitting here, and then the sample is stretching this way, so you will not lose the field of view. The field of view always stays here. That's the essential part.
What is the scale, linear scale?
I'm sorry.
What is the linear scale? How big are the screws or images or anything?
Oh, the scale. The scale, for example, this one, here, the length here is 7 millimeter. So this is 7 millimeter. Okay, there's another one. Unfortunately not. We cannot do you mean stress? I mean, or strain? Stress. The global, I mean, the averaging stress, the stretching can be measured. Yeah. Strain, it's a difficult thing to measure. Okay. Using this holder, we try to stretch the sample. This is a gap of the cartridge, and then using a good camera, and then this is the sample based on the isoprene rubber cross-linked, and then silica particles about this corresponds in about 15% or so volume, inside. Okay, so I will stretch this sample this way first for this magnification, and then the movie changes to the magnifications. So from 3,000 to 10,000 and 20,000, it's going to be magnified and magnified. Okay, so we start to stretch. The light gray part is rubber, and then the dark gray part, although it's not visible so well, those are the silica particles. So we're stretching this way now, and then it's now 10,000. You can see the particles even more clearly because we have a larger magnification. In this case, we stretch this way, okay? And then this is now 20,000. And then the sample has destroyed, somewhere not in the field of view. Somewhere, it's being cut or, So important thing is that, towards the end, there are very bright places. Light looks like white. See, like this. There are white places. Those are the nano cavity. In some cases, we do the same thing. We end up with this type of a movie. Strange movie. It turns out that we are looking at this place, and it's been damaged. It's been crossing by the electron beam, so that nothing moves. And then, but the place where we don't shine the electron beam, it's stretched like crazy. Okay, so we need to be careful about the beam damage too in this case. Nonetheless, these are the sequential image, and this is a quiescent. I mean, the strain is 0, and then strain is 5.56, 64, 73. Okay, as you can see, there's a void formation here and there, and this part, for example, this appears to be connected in the beginning, but as you stretch a little bit, it's separated, and then start to form a void over here. And the red point is the same thing. It appears to be connected, not so much compared to this, but it soon depart and then have a void. So that seems to be a fundamental mechanism of void formation. And there's another type, the yellow one. So this been connected, and the void, start to form right in the middle of this connection. I mean, aggregate. Yes, please.
I have a question. For me, there are two different mechanisms. One, the pillars are going away from each other, and this is the blue
Yes.
behavior, and the red behavior is the contrary. The carbon black pillar or the silica pillars go back, and then void occurs around this path. So for me, there are two different.
Okay, maybe two different, three different. Yeah, depending on how you look. For me, these two look similar, but maybe not so. Okay, anyway, so thank you. And this type of void formation reminds me that the simulation, we have aggregates, and when we stretch, inside the aggregates, we have a stress concentration, and then that's probably the reason why we have a void right in the middle. So anyway, we have a stretching experiment, and then we have a void formation visible under the microscope. Yes.
So I have three questions. You just mentioned that the strain is difficult to measure.
we can measure stress. We cannot measure strain. That's a stress. Yeah.
Okay, and the second question is, can you measure the by PCB using this technique?
What is?
By continuous phase.
Yes, you can do that. Yes.
And you need to dye, for example, dye some of the network.
If you dye means staining,
Yes.
then you better not to stain the sample. So you need to find a way how to observe the sample under unstained state, like some sort of a contrast enhancement also. Once you stain, then it's a different story, I think.
Probably I imagine the stain can't go through the sample. So
Mm.
once you stress, the unstained survey will expose, so you will make.
That could happen. Yeah.
And then, are you able to use this technique to construct a 3D structure?
Yeah, you can. This holder is designed so that we can do this tilting.
But surely, when you tilt, it is at a different strain. So it's that even time point. But you need to construct a point when it's rotated at a single point, but the point moves.
It depends on how big the field of view. The gap is like a micron size, and then your field of view is very small compared to that. So I think essentially, I can assume that's the same thing. Yeah. Yeah, please.
This is strain, right?
This is.
Initial, like the change in length over initial length.
Hmm?
Change in length over initial length, for example.
Yeah.
Yeah.
Yeah. So from this data, what we can do is that we can measure we can stress and I sometimes confuse stress and strain. Okay, we can measure, actually try to measure the local strain. Okay. Sorry, strain. Okay. I sometimes mix up with strain and stress. Okay, this is strain. Okay, so in the 2D image we mark points, and then to make a triangle like this, and then as we stretch it, this triangle deforms, right? So you have all these coordinates, and then you can measure actually using this type of relationship. You can measure the strain along the x-axis. Y-axis is the stretching direction, and then shear strain. Okay. And further, we can do the diagonalization, and then to make the shear component 0. Then that would be the maximum principal strain and minimum principal strain. And then normally, it's not the direction of the strain is maximum strain or minimum strain is not x and y. So the stretching direction is different from the maximum strain direction, but normally, it's quite same. So we do this kind of analysis for this stretching experiment. We can have these tiny triangles. We make that, and then poor student follow this position, as a stretching. He finds the same position at a different strain, and then calculate the local strain. Okay. So the global strain is up to 0.73, but as you can see, the red part somewhere here, it's over 2.5, and there's some places the stress is essentially 0, and the part where the stress is strain is 0 is that's the aggregate position, and then those red part, are often between the aggregates. So it's difficult to see now. So this is local strain map at the strain of, I think, 0.73 or so. Okay, so as you can see, the zero stress, almost zero stress is aggregates, like here. And then there are high strain region, mostly between these aggregates. So that's what we can observe. Okay, so this is purely an experimental result. Local strain map we can build. Again, we can hand this data to the computer simulation people, and then they can do finite element analysis again. So what he has done is that he chose the initial structure at strain 0.48, and then in the computer he stretched the structure up to 0.73. The reason he has tried to stretch the sample from 0 to 0.73, but it didn't. It's a mess. Okay. The finite element analysis you can apply for just small strain. Okay. So it end up with the starting point is 4.8. So that the difference is about 0.25 or so, right? So it's a small stretching. Nonetheless, if we do this, then this is the picture, after he stretched. So the position of this aggregate should be matched with this, and then we overlay these two, and then it's fine. Okay. So in this 0.25 strain, it seems like that finite element analysis works. So this is a strain map. And the good thing about the computer simulation (FEA) is that he can calculate the stress map. Okay, this is stress, this is strain, and then let's talk about the strain first. Okay, the position where he has a very high strain is somewhere here, and then you can take a look at compare these two, and then this red position is almost the same position as there. Okay, so and then we look at the stress map. It looks different. It looks like the high strain part, which is a red part in this picture, is sort of connecting these aggregates, and then try to have a network. So it's like a stress network in a sample, and then these rubber domains don't do anything. They just don't do anything. When you stretch, the force is supported by these network stress. I'm sorry, net stress. So you can actually visualize how the force is yeah, please. I'm the wrong person to answer that question. Sorry. I think it's a basic in Japanese it's a kose hoteshiki. Yeah, what is that in English? How do you say kose hoteshiki in English? Do you don't know? I don't know. That's there's a basic equation, right? And when you stress, then how you calculate, the and I mean, if you apply strain, then there's an equation how to calculate from strain the stress. I don't know how to say that in English, but I think he uses standard type. He doesn't do anything strange or anything particular.
Hyperelastic models?
Yeah, that's right. Yeah. So it's very conventional. I heard it's a very conventional FEA. No, it's not isotropic. Yes. So how he divide this rubbery part, for example, into triangle is crucial. Yeah, but sorry, I'm not the right person to answer that question. Okay, this is a stretching experiment. Sometimes this is a very low Mach image. This is a gap of the cartridge, and this is the sample. In some cases, we find a hole in the sample, and then we further stretch it. Then we can observe the crack propagation under the TM. We have actually done that. I have a movie there. So this is another rubber composite. Then we found this crack, and then try to follow how this crack propagates in the rubber composite. And it's not so simple. It goes and it stops, and it goes and it stops. It's like stick and slip type of behavior. And we also analyze this kind of data with a local strain map. Okay, but for those who are interested in this, there's a paper here. So in order to go to the next, please.
If you have a natural rubber, will you see the crystallization close to the tip with this kind of technique?
Yes. Separate for this experiment, what we are trying right now is that we have a natural rubber or isoprene rubber without any filler, and then we stretch it like a strain 4 or 5, and try to do the mapping that I'm going to describe in the next session. Then we know, at the high stretching, how much time? 10 minutes. Okay. Where the little crystal forms, and then how this crystal evolve. That's an interesting experiment. We are doing that. So in order to do that, I need next technique. Okay, I have only 10 minutes, so I'm going to go very fast. Okay, this is again published in Macromolecules last year. So for detail, please refer to this. I only talk about the essence. Polymer crystals. I probably don't have to explain this to you, right? That's everywhere. In your PET bottles, we have crystals, and introducing a crystal and then controlling the size and the distribution of the crystal, the mechanical property differs. So it's important. So the basic idea of the crystal is that we have a chain, and then under the crystallization, chain aligns and then make a lamellar crystal like this, and then they stuck together. So it's going to be a stuck lamellar structure, and then these stuck lamellar structures somehow self-assemble and then make a higher order structure like a spherulite or sometimes shish kebab if you have a high stretching, right? And in order to understand the structure, people use this often scattering technique like X-ray, neutron, light. For this higher order structure, in a microscope, they use optical microscope and cross-polarize. You know that very well, I hope. But smaller structure, between here and here, that there's not much knowledge, So the question is how this stacked lamella, aligns in a space to make this higher order structure. It's not so obvious. We would like to image that. Okay, so there's two ways: using X-ray or using electron. Okay, X-ray. Even though you go to the big facility, the beam size is down to typically 1 nanometer, maybe a little bit more, a little bit less. I ask synchrotron people, then we can say we can go down to 200 nanometer, but I don't believe so. So, but they say 0.2 micron, okay? But even though it's a 0.2 micron, if there's a crystal like this, then it's too big. Whereas electron microscope, as I talked about, that we can finely tune the beam so that the beam size can be nanometer size. So if we use this beam and this beam, then probably using the big beam, then the alignment of this stacked lamella would be something like that. But with the electrons, you may be able to find a finer structure. So that's what we want to do. Again, we have to take care of this problem. This is old data from Kyoto University. They use a single crystal, normal paraffin single crystal, and they shine the beam, and then with how much dose the electron diffraction disappears. So this is the one reason why people have been doing electron diffraction in 60s and 70s, but this is so tedious to take a diffraction under the electron microscope. So they move all of them move to the X-ray scattering. That's a history. Now we can have a very good camera with 5 more minutes, right? Yeah, we have a very good camera so that we can reduce the dose quite much. Then we can do this kind of experiment. Okay, we focus the beam, and then we take diffractions from each spot of the sample. So each spot we have diffraction like this. So if we have 200, then we're going to have a two-dimensional diffraction image of 40,000. That's a big data. So that's a basic idea. So we prepare polyethylene crystals, and then we raise the temperature up to melting point once for 5 minutes, and then cool down to the below the melting point, 80 degrees, and then stays for keep it for 10 minutes to crystallize. That's one sample. We suppose this is the crystal goes everywhere. That's a non-oriented sample. Part of the sample we stretch it like this for five times. So assuming that the change is going to stretch this way, right? So 2 samples. And again, for the stretching sample, we cut this way, and then we microtome. So what we essentially show you is that the cross section of the sample. Okay. And now we do electron the imaging, what we call nano diffraction imaging. Okay. So we focus the beam down to 15 nanometer. In the paper, we write 15 nanometer. That was wrong. I'm sorry. When you happen to read our paper, it is 6 nanometer. That's a miscalculation. Okay, so because we thought it's a 15 nanometer, so the step length was we set 30 nanometer, so very low resolution image. But anyway, so we take, like I say, we shine the beam and take the diffractions. And then total dose is this much. So this is a very small dose to image the whole area. Okay, not in the individual one. So let's skip this for the time's sake. This is one example. This is a oriented one. We stretch this one, and the stretching direction is this way. Okay, and this is a stem, bright field stem image, and this is not the structure. This is the supporting membrane. So this is not the structure. We don't see anything. Unfortunately, we don't see anything, but we see diffraction. So this diffraction corresponds to this position, and then we scan the beam. We scan the beam, and then this is the corresponding diffraction pattern. Because the sample is stretching that way, so mostly we have a diffraction in this position. Sometimes it moves back and forth, but mostly here. Okay, so that's one thing. And yeah. Okay, so for the non-oriented sample, we do the same thing. So the diffraction varies very much, right? So that represents that the chain orientation is sort of random. Okay, I spend much more time, so I just go to just skip this part. We get many types of the diffractions on. So depending on the type of the diffractions, we can assign how the chain, I mean the lamellar crystal, oriented with respect to the beam. So there are different types. Now for the oriented sample, stretching this way, we took this 110 or 200 peak. We focused this peak, and then that's because the chain direction is perpendicular to this line from this diffraction. We know that, so we only focus this beam, this position, and then we draw. We try to measure the chain orientation. So if the chain is oriented this way, which is similar to the stretching direction, then it's blue. Okay. If it's perpendicular, it's red. So some spot we cannot identify these two spots, so that's a black. Okay, but you can see this is almost all blue. That means the chain is aligning this way, as we expected.
But this is not the chain, these are the lamella.
Lamella, yes, lamella, yes, sorry. This is for the non-oriented sample, same way. So it's random, as we expected. So what I want to say is that each pixel has a 30 nanometer resolution, and in this particular case, with the resolution of 30 nanometer, we can define the orientation of the lamella. That's the conclusion. Okay, we can extend this technique to, for example, apply to the rubber stretching induced crystallization. Of course, we can increase the resolution, because we mistakenly thought that the beam size is 15, but it was 6. So we can at least do the 6 nanometer imaging, but we can tune the optics a little bit more, and then the beam size diameter is now 1.4 nanometer, and then step size is 8. Then the image looks dramatically different, like this. So this is unstained. We don't stain anything. This is unstained. The contrast is from the diffraction. Okay, so the bright part is highly crystallized, and the dark part is not so highly crystallized. So as you can see, there are many. I think these are the individual lamella crystal, and then if we blow this up, then we can see each lamella like this. And not only the picture, but each pixel has a information of the chain orientation inside the lamella crystal. So we haven't complete the analysis yet, but eventually we can determine, in this stacked lamella, how the chain is located inside the stack. Okay, and then this is a comparison. This is the same sample, ruthenium tetroxide stains sample, TM image. So these are quite similar, right? So I think we are able to see the individual lamella right now. Okay, with that, I finish my talk, and then thank you very much for your attention.